Okay, just before we get started with the lecture today, I'm going to give just a couple of housekeeping announcements. By the way, this is the most students I've ever had for a second lecture, so pat yourselves on the back for being part of that record. Really quickly, in order to sort of solve the office hour issue, I am just moving my office hours from 4 to 6 p.m., okay? So that means it overlaps 2 different slots. I know it's not a great solution. People don't want to stay here after 5, but if you are, you know, if the assignments due that night, you'll probably stick around. So that's what I'll move my office hours to. And if I find that not many people are coming after 5, I'll probably just change it to 5:30 or something like that, so people can sneak in before they go home. So that's the first thing. The second thing is, okay, so now that we've had the first lecture and I've put some links here, so you can kind of see how the class is going to work. So if you click this YouTube video, you'll come over to the video for last lecture, and you can see down here on the timeline, I typically put in timestamps for things. So those timestamps are visible not only in the timeline right here, but if you scroll down to the video description, they're all listed right there as well. So if you want to jump to a particular topic, please do that. But the first time you watch the lecture, please watch the whole thing, because I get some people who are like, oh, that doesn't seem interesting, and then it ends up being on the exam. So just because there are chapters, use that for like studying, but make sure you watch every part of every lecture to make sure that you caught everything. And if you click on the link to the PDF here, what you'll get, and so there are 2 class shells on D2L. So I mentioned this in an announcement to the 6980 class, but if you click here, you're going to go to the 3200 shell. And the only reason I did this is because there's more students in 3200. And so for anyone in 3200, you'll be taken directly to the slides. But the people in 6980 don't have access to that. But if you just go to content and then lecture slides, they'll be listed there. So the people in 6980, unfortunately, can't just click on that convenient link. You're going to have to go to the 6980 shell and then open up the content. But the slides are there for you. I just didn't want to have 2 links here because it looks messy. That's it. Okay, any questions or anything about any of that? Perfect. So just to give you an idea of what's coming up in the course, so we got through the intro lecture. These 2 lectures here, lecture number 2 and lecture number 3, are probably the densest lectures in the course. Not dense in terms of stupid, but just in terms of I'm throwing definition after definition and a lot of terminology at you. And that's so we can get that out of the way and we can start with the fun stuff, which is the algorithms and the programming of the assignments. In my opinion, anyway, that's the fun stuff. So if you don't get absolutely everything and you don't retain every piece of information as I'm speaking it to you, that's okay. That's why the slides are there. That's why the notes and the video are there to go back and study it. But just realize that I'm going to be throwing a whole bunch of definitions at you. And also realize that wherever I give a definition in a slide or in a lecture, that's a really good hint for the exam, right? So definitions, algorithms, stuff like that are really good exam questions. So these 2 lectures, you're definitely going to see some questions from these 2 on the exam. So let's get started. All right, lecture number 2, agents, actions, and environments, all very important stuff. And so as I just said, this is probably the most dense lecture. And if you don't understand all of it or don't follow along right away, it's okay. We will be talking about all of this stuff in later slides as well. So all of these topics will come up constantly during the lecture. And use the slides as a reference, of course, because they're available to you. So first, what is an agent? This is going to be one of the most important questions of the class. An agent, not an FBI agent, right? FBI agents are agents, but a more general definition of agent that we'll be using in a problem-solving AI context is just a thing that exists in a specific environment. We'll talk about environments in a second. The agent is the entity for which we want to make decisions and take actions. So AI is all about making decisions, and those decisions typically are something like, which action should I take? There's going to be some forms of AI where a decision might be something like, okay, that's a picture of an apple versus that's a picture of an orange. That's not necessarily an action, but we are talking about actions in this class. So in most cases, what's going to happen is that the environment defines a problem. So for example, we could have, I don't know, the road, so a self-driving car, that defines the problem. Or a chessboard defines the problem. And the agent is going to be a possible solution to that problem, right? So I'm going to take actions and make decisions in order to try and achieve some goal in that environment. And there are many, many, many different types of agents, and they're all equally valid. So this is a Roomba. Who here has a Roomba? Does anyone have a Roomba? A couple people? Yeah, I've never had one, but I've heard they're pretty good. And so the Roomba is an agent, right? It's a thing making decisions on essentially what voltage do I apply to my wheels in order to go around, right? So there's some algorithm in that Roomba that somehow scans its environment, or maybe it just goes forward until it hits something and then it turns in a random way. But that is an agent in an environment, probably with the goal of make the room a little bit less dirty, right? Here we have a little bit more complicated agent. This is Spot by Boston Dynamics. We won't be going this crazy in this course talking about how to control robots like this. If you're more interested in robotic-specific mechanics, we do have some excellent robotics courses in the department, but that's not what we'll be doing here. But this is an agent in an environment trying to solve different problems. Those are real-world agents. Not every agent is a real-world agent. Here's another example. So this is an example that's very popular in reinforcement learning. This is the balance cart problem. And so this is let's see if I got something over here. I don't know, what is this? Okay. So what you're trying to do when you try and balance something is that you're not perfect, right? So it's going to lean to one way or the other. So if it moves to the left, I've got to move it to the left, move to the right, etc. So that is a simulation of that problem. And the goal here is to balance it as long as possible. And so we'll get into this, but this is an episodic problem, where there are episodes, so how long did I keep it up for on the pole on the cart? And so we're trying to maximize that amount of time, or maximize the amount of time that this pole is being balanced. And so this is a 2D representation where our actions would be move to the left and move to the right. And so there'd be some fixed speed. And then this simulation, you could use it in machine learning, or you could do all sorts of different algorithms to try and solve this problem. But we'll see this again later when we talk about reinforcement learning. Here we've got the game of chess. And so when you talk about games or some environments, we actually have to make a decision. What is the agent, right? Like, what is the agent here? Is it one of the players? Is it both of the players? Is it the pieces on the board, right? And so talking about what the agent is in this example, it's not the individual pieces, but it would be the player. So the player is the thing that's making the decision. But if we have an example like a video game, let's say our boss at the video game company has told us it's your job to make an AI to control Mario, right? So in that case, over here, the agent would be Mario, trying to say, okay, when do I run, when do I jump, when do I shoot fireballs, etc. But over here, in this case, maybe we are the programmer for the Mega Man series, and we're in charge of writing the AI for this dragon that's chasing the player around, right? So you always have to define what the agent in the environment is, and then what you can do to guide that agent or issue actions or make decisions is all based on the context of that agent, right? So some agents may have actions that are possible that other agents don't have. And so an agent within an environment will take actions to achieve a particular goal. And those goals are typically given by humans, right? You don't just have a machine typically appear in the universe with a goal in mind. Like the Roomba is given a goal by the human. Mario is given a goal by the human. And so typically our feedback or our input to these systems as humans is, here's the problem I'm trying to solve. That problem involves an agent, an environment. Here's the actions you can take, and here's the goal that I want you to achieve, right? Get the minimum path or the shortest distance path to this thing. Get the most points in this video game. The agent perceives its environment somehow and makes a decision about which action to take. Depending on the agent, depending on the environment, you are going to perceive the environment in different ways. And so, for example, right now, I am perceiving this class with my eyes, right? There are some things that I can see. There are other things that I can't see, right? So one decision I might have to make is like, I don't know, in what order do we get out of here in case there's a fire? Well, there's some things I can't see. I can't see, like, for example, Is everyone able to walk or run? Are there book bags in the way? So our perception of the environment is going to inform our decision making, but it's not always complete. Like, I can't see what's outside that window because the shades are down. The agent is going to take some actions, and those actions are going to change the environment somehow. So if if my goal is to leave the room, then my actions would probably be movement. And so if I take an action, right, now I've changed the environment because I'm in a different place in the environment. If I had moved into somebody, maybe I knock them over. Maybe that's a bigger change, right? If you shoot a fireball in a video game, maybe you've destroyed something, and now that's no longer an obstacle for you. So actions change the environment somehow. And then typically, with these problems, it's not just a single step. Like, we'll take an action, and then at the new state, we'll do another thing. And so this process repeats and repeats. So artificial intelligence really is the algorithmic discipline of making these decisions more intelligent. And intelligence here essentially is a measure of achieving goals, right? So if it has achieved the goal, we deem that to be pretty good as an evaluation measure. So here are just a little diagram. We have our environment up here. We have our agent down here. I've drawn these as separate, but the vast majority of the time, the agent will be inside the environment. But this is nice to separate them for this particular diagram. So agents are going to make some decision. Those decisions will result in actions. The actions will affect the environment somehow. And then the agent will, after they've taken an action, they'll then look at the world again and say, what is my new perception of the world? And then based on that new perception, I'm going to make another decision. Okay, so this is just a loop that repeats. And how long this repeats is completely dependent on the context of the problem that you're trying to solve. So agents perceive its environment through sensors, right? Oh, we have a question?
I just wanted to clarify. So by perceiving, you mean understanding or just raw data?
I'll talk about that in, like, this slide is talking about that. Yeah, no, that's okay. So an agent is going to perceive an environment through sensors. And again, a perception is like, what do I believe about the state of the environment that I'm in, right? So if the game or the environment here is me trying to leave the room, maybe I have to go to the bathroom, then there's a bunch of things in this room that I don't really care about. But there's some things that I do care about. So I would care about, are there any bags in the way? Are there any people in the way? Where are the chairs in the room? But other perceptions that I may have, like the color of the wall, that doesn't really matter for my goal of getting out of the room, right? So we're going to gather information somehow to well define the problem, because if you've ever written a computer program, in order to make a decision in a computer, you've got to really well define this problem in a way the algorithm can understand. And so if you have a robot, the perceptions may be a camera, maybe it has some audio or visual input, maybe it has a laser for detecting the range of something, like how far are you away from me. Maybe it has sonar for detecting longer distance stuff, etc. Humans, we have these, 5 senses that we can use. Oh, okay, maybe my vision is damaged, so I would have to feel around or something like that. We're gathering information from our environment. But in a video game, for example, maybe our sensors in the video game are things like, okay, if it's a 3D game, maybe we give the agent, like, what's on the screen, and then it could read what the screen is. In this course, we'll be doing much simpler things. So we may, for example, let's say we want to construct an AI to play the game of chess. We would just give it the chessboard directly in RAM, right? Here's an 8x8 array with all the pieces in the board. And so, yes, agents do perceive their environment, but many times when we're talking about games or simulations or research, we're just going to give the robot the specification, right? And so maybe you have an agent that you've given a perfect world in simulation, but then when you go out into the real world, okay, now you have actual data that may be like noisy, like sensor data. Maybe there was something occluding the vision or something. So depending on the environment, depending on that, you would give the agents information in different ways. And then the agents are going to act on the environment via actuators. And so actuators are different depending on the agent. So for example, if you have a robot, an actuator is anything in which it can interact with the environment, right? So I'm going to move around on wheels. Those are making physical contact and interacting with the environment. Maybe you have arms. You're moving around pieces on a chessboard or dishes in a sink or something like that, whatever you're doing. Humans, we have limbs, we have tools, lots of different ways we can interact with the environment. In games or simulations, again, it's a weird way, an action, an actuator, there's no like virtual arm picking up the chess piece. Our actions would be just a function, right? So we have an environment with some variables in it, and then we have a function which acts on that environment and maybe moves the chess piece or moves the robot over. And we also may have some knowledge about the environment as well. So the agent may have knowledge, it may not have any knowledge. And we'll get into this when we talk about search algorithms. If the agent does have knowledge, this is called informed search. And if there is no knowledge, that would be called uninformed search. And so the algorithm that you choose can incorporate knowledge, or maybe it doesn't incorporate any knowledge. And I'll give some examples of that in a second. So a percept, essentially a perception of an environment, is the agent's perceptual inputs at any given instant. Okay? So essentially, it's the agent's current belief of the world, or what we will use from now on. We're not going to talk about percepts or any of that anymore. We're just going to talk about the environment's current state. So this is an instantaneous state of the environment. So in this course, even if we're talking about a problem like a self-driving car or a video game or something like that, computers have to work on data that exists discretely, right? So at some time when we're trying to make a decision, we have some snapshot of our environment. We make a decision based on that. So if we're driving a car, maybe we can say, okay, our processor is fast enough to process 1 image per second or 100 images per second. But no matter what you do in any form of AI, you essentially have to break the real world into discrete time steps so you can actually do computing on it. As far as I know, no one is doing any sort of real time. Now, when we say real time, it usually just means really fast, right? So maybe this algorithm can react in a millisecond or a nanosecond, but it's still discrete time steps. And what we believe about the environment at any of those time steps is the state of the environment. Yep.
So this taking environment state as a state of agent's understanding of the world takes out the question of interpretability, which we as human beings do.
Yeah, that's not really an issue. We're going to be, in this course, we are going to assume that we're working with complete knowledge of an environment. So we're not working with, what are the chances that there's something over there? We'll know for sure. So we're working with deterministic, environments.
But more so like if you're taking sensory input, how you choose to give it meaning, doesn't that get into the side of like what creativity is, and if you want to model that?
Yeah, we're not getting that deep. The next lecture we'll talk a bit more about that. And so I want to solve a particular problem. I am going to have to come up with the representation for all of that, right? But that's a feature of the problem you're trying to solve. But in the end, you'll have states and actions, and so you'll have to come up with that somehow. There's also this concept of a percept sequence. And by the way, all this terminology comes out of the optional textbook, the Russell and Norvig textbook. It's an excellent textbook. I recommend reading along with it. It's not required, but that's what they call it. And what a percept sequence is, it's essentially a sequence of states throughout time. Or it's the complete history of everything that the agent has perceived so far. So in general, if you talk about every possible problem in the world, an agent's choice of an action at any given instant may depend on the entire sequence of percepts up to that date, right? And so what you did in the past sometimes matters. In this course, when we talk about algorithms and solving problems, we're only going to be looking at problems where the current state is sufficient, right? Because we don't want to open up that whole can of worms that is complete state histories. And so we'll be talking about fully observable states, meaning that we can see everything, and no state history is going to be required. And so the agent's behavior is given by the agent function. And that is going to map a given percept sequence to an action. So this is what we're doing every day, right? Given the history of everything we've ever observed, make your next action, right? So as humans, we're probably not making actions like every 10th of a millisecond, but you're making decisions, maybe I have to sneeze, maybe I have to go to the bathroom, whatever, maybe I have to study. And so the process of making AI is essentially writing agent functions, right? This function takes in a state, maybe a time or some other parameter, and then produces an action. Okay, let's look at an example of this. This is an image. Someone raise their hand and tell me what will be different about this image if I had taken it 1 second later. Yeah? Okay, why? How do you know that? How do you know gravity? It's not trick questions. I'm just literally asking you questions. Well, how do you know about gravity? There you go. So you have some knowledge, right? So you've looked at this, I've asked you a question, and you've applied knowledge to it. That's a perfectly normal human thing to do. But where did they jump from? Where were they a second ago? Maybe there's a trampoline you can't see. That's probably not the case, given our knowledge of how the world works. Maybe this person jumped from here. Maybe they jumped from a helicopter. Maybe there's a string you can't see, right? There's a lot of assumptions here. And so let's say the problem is I'm the leader of a fire department, and I'm trying to train my firefighters to hold a big mattress or something for people to fall on when they're in burning buildings. So this is a training scenario. How do they know where to put the mattress? Right? If you just give them a picture, the whole point is you can't know, right? There are other variables here that you need to know. And those variables are given by the sequence of actions. So if you take this one right here, and now you've gotten this whole sequence, you can tell, okay, this person definitely jumped from right there. And even, like, if you have 5 minutes of physics education, from here to here, you could probably assume this person is a certain, height, and then extrapolate how far they've fallen in that amount of time, and you can actually get the speed from that, and so now you can position things, etc. So this is just an example of, even though we have a lot of knowledge about something, sometimes assumptions about knowledge may not be correct, right? And so you don't want to take, that's one of the things. The other thing I'm trying to say is that sometimes the entire sequence of events is necessary. But in this course, we will not be dealing with problems that are this hard where you need the entire sequence. We'll be dealing with problems like chess. Okay, so believe it or not, if you walk into any chess game at any point in time, if there's all the pieces on the board or only 2 pieces on the board, you can still look at a chessboard and make the optimal move, even if you don't know what has happened up to that point. So the best move possible on a chessboard is not dependent on the previous sequence of actions. It is only dependent on the current action. And now, there's a little wiggle room there. Sometimes there's a rule in chess, if you repeat the same move like 10 times in a row, it's a draw. But if you throw that out, you can just, yes, someone who's very good at chess or a computer or an algorithm could look at this board and give the optimal action. Here's an example where that's not the case. So this is a game of League of Legends. This is from a long time ago, so the players probably don't play anymore. But what's happened here, this is a game where there are 5 players on the blue team and 5 players on the red team. And the blue team is currently trying to kill this objective called the Baron. You can see the hit points going down over time. And what happens here is that the team who deals the last hit point of damage to this creature gets a huge amount of gold and a huge buff that makes them stronger, etc. And this guy just waltzes in and shoots it at the very last second and steals it, right? Why would this team let him do that? Why did that look so easy? Well, here is actually what that other player saw. They saw nothing at the time that they were able to shoot it. So how did this player know when to shoot? Well, you can see down here, there's probably like a little vision ward down here. And so maybe 30 seconds ago, this player said, okay, they're walking in to start fighting this thing. I approximately know the amount of damage that they can do at this level, so there's lots of knowledge. And then based on whatever prediction they can do in their head, they're going to say, okay, in 20 seconds I'm going to shoot this rocket and hope it blows up the thing. And, most of the time, he got pretty lucky. Like, he's not a god. He doesn't do this every time. But in this case, it's another good example of the history of the minute or so leading up to this is very vital into making that decision of when to fire. You can't just take that black screen and know when to shoot, right? So that's just another example of needing the entire sequence. Yes?
So in the percept sequence, you said that all the percepts are recorded in there that have happened, right? I was just wondering if there's any way of like ranking important ones, and maybe there's a lot of useless ones as well, right?
But that's like, so that concept is not applicable to just the definition, right? So that's like a whole other topic that would take a long time to explain. Yeah, so I'm just trying to say that there are environments where you only need the current state, and there are environments where you need every state. And so typically we deal with the worst case, not dealing with, okay, some of these may be important, some of them may not be important. It either does or doesn't require all the actions leading up to this state. Okay, so now we know what an agent is. What is an action? So an action taken by an agent in a given state transitions the state to another state. So we call them state transitions, go from state 1 to state 2 to state 3, etc. And so here's an example you may have seen. This is a state transition diagram, and this is a state transition table. So over here, this environment is so simple, it just has 2 states, right? And the actions are so simple, there are only 2 actions. So if we look over here at the state transition table, it says if we're in state 1 and we take action 1, we stay at state 1. If we're in state 1 and we take action 0, we go to state 2. If we're in state 2 and we take action 1, we stay at state 2. Or if we take action 0, we go to state 1. So if we read this, we can say, okay, essentially state 1, or taking action 1 keeps us in the current state. Taking action 0 transitions us to another state, right? So if we look over here, this is the visual representation of that, where we have state 1. Okay, action 1 keeps me at state 1. Now, the distance between these nodes in this graph and the distance, like shape of the edges, doesn't matter at all. It's just a visualization. So if I take action 0, it takes me to the other state. Same if I'm at state 2. Action 1 keeps me here, and taking action 0 transitions me to the other state. Now, the environments that we're working on aren't always going to be this simple, of course, right? Here we can represent this by a state like a table, but you know, if we're playing Super Mario Brothers or we're looking at Google Maps, it's not always a table. Actually, Google Maps is a terrible example because you can represent that as a table. But some environments like the real world are going to be much more complex than just a simple table or a simple state transition diagram. Yeah, please mute your phone before that happens again. Okay, so it takes an action taken by an agent transitions the state to another state. And then we have, so this is done by the state transition function. So the state transition function, or STF, this is called the successor function sometimes, but it could be an arbitrary function. It could be a table, it could be a graph, but in general, we just think of this as an arbitrary function. So this function is going to take in the current state, S, that is the current state of the chessboard or my current belief of the environment. Then it's going to take in the action, and the result of this function is going to produce S prime, which is the next state, right? So something may be built into this state, to this STF that says, okay, we're working in 1 second increments or 1 millisecond increments. That's not really important right now. What you know is that this function takes in the state, it takes in the action, and it just produces the next state. So in this case, that STF was given by a very simple table. If you're playing a video game or you're doing some robotics, there may be some physics calculations that say, okay, I'm currently at this state, here's my velocity, here's my acceleration, so it would have to calculate something. So this can be an arbitrarily complex thing. So some examples of actions. This is a jumping jack. It transitions you from an unhealthy state to a healthy state, right? No, so it like physically moves you around. Maybe there's like a dog who runs by, you accidentally touch it or something like that. The actions affect the environment. Here's an example. We're going to be playing this game. Who's played Connect 4 before this game? About half the class. So here's an example. This is a board game. I'm not going to go into all the rules, but you essentially drop pieces into a physical board, and they slide all the way down, and your goal is to get 4 pieces of your color in a row, and then you win the game. And so over here, for example, if I take this state of the board and I choose the action of putting a piece in the top here, it will go all the way down, and then I'll result in this state. So I take my STF, I pass in this state, I pass in this action, and it will produce this new state. Okay, so that's a really good example that we'll be using in the course. In a video game, my action is going to be a combination of buttons on the controller being held. So in this, probably the most simple possible case is that if I'm just holding right on the controller, what's happening? Well, the video game is going to say, well, here was my state on the last frame of the game. And then if this is running at 60 frames per second, then approximately 16 milliseconds later, that's 1,000 divided by 60, I'm going to be a little bit more to the right of where I was on the last frame, right? Other things may happen. Maybe I ran into an enemy and I died or something like that. Maybe I collected a coin. But essentially, this move to the right action is going to affect the environment by changing the position of the player. Almost the exact same of that is like moving a piece on a chessboard. I've taken an action, E4 to D8 or whatever action that you want to take, and then the new board is going to reflect that. Now, when we talk about games or environments like chess, we are also going to get into things. We're going to talk about legal actions and illegal actions, right? So, for example, in a video game, I can do whatever I want at all times, right? I can always hold right. Now, if Mario is like walking into a pipe, maybe he won't move anywhere, but the action is still legal. But in a game of chess, for example, I can't start a chessboard by capturing their king with my pawn. There are rules to the game, right? And so some actions will be possible, other actions won't be possible. So you'll have to have some sort of logic in there that say, oh, it's like an is legal action function. You can test whether or not this action is legal at this state. Fighting games have lots of actions. You can see here that you can have many hundreds of actions per second put into these fighting games. It can be as arbitrarily complex as you want. But typically, when you're talking about actions and you've discretized a problem into discrete time steps, it's going to be whatever the combination of button presses I have right now, that's my action. If you're talking about robotics, it's whatever combination of voltages I'm applying to all my actuators, that's the action that you're taking at that time step. Next definition is a policy. And a policy is a map from states to actions, right? So it's essentially a big lookup table or a function or a neural network or whatever. And so, this is weird. I'm going to have to fix this. Whatever font the PowerPoint chose to display this in, this is supposed to be the pi symbol, like the Greek symbol pi, 3.14159. So I'll change that, but policy is represented by pi. And the optimal policy, meaning that if we were omniscient and we could know everything, every possible outcome, the optimal policy would be the best knowing the best action at every state. And if we knew the optimal policy, that would be pi star. And through this course, we're going to be doing a lot of things which are like C star, H star, pi star. That essentially just means the best possible thing. So pi of S equals A. So this means given a state that we were in, state S, do action A. All right, so this policy could be the agent's current policy. It could be an optimal policy. It could be the do nothing policy. Like, let's implement the do nothing policy right now. Right? Time is ticking along, and I'm choosing to do nothing at every step. That may be legal. It may not be legal. In the game of chess, there is no null action. Right? You have to do something at every time step. And so this policy is just a mapping from every possible state in the environment to an action that you should do at that state. Whether or not you can store the entire policy or it's a function or a neural net, that is up to the complexity of the environment. So it could be a lookup table, could be a bunch of if statements, arbitrary function calculation, neural network. The policy can come in a number of different ways. Here's an example of a policy, and we will be doing this in one of our assignments. So this is a pathfinding problem in which the white squares are sort of open areas in the environment. The agent is the red dot, and the agent can move up, down, left, and right, and they are blocked by these dark squares. And so the objective here would be, okay, maybe I want to get to the nearest green cell as fast as possible. right? So what we've visualized here is a policy. So these arrows that you see, they are saying if the agent is in that state, here is the action that they should take. And sometimes more than one action yields the optimal result. So for example, over here at this state, I could either, move left to get to this green one, or I could move down to get to this green one. It's going to be the same distance. And so sometimes policies are deterministic, and sometimes they are stochastic, meaning 50% of the time, if I choose to go left, 50% of the time I choose to go down, I'll still get the same exact result, right? Maybe I'll go to a different one, but my goal isn't to get to a specific one, it's to get to the nearest one. So this is an example of a policy. I've created a mapping from states to in general, it's a probability distribution over actions that I should take at that state. Here's another example. Who here has played blackjack, the card game? A few people? Oh, we've got a wholesome bunch here. Only like 10 people know blackjack. We'll get to know blackjack because it's a very good example for reinforcement learning later. But essentially, blackjack is a game you play at a casino against the dealer. They deal you some cards, they deal some cards, and you're trying to get as close to 21 as possible without getting over, right? And so what this table represents is that if you have these cards over here, and the dealer is showing this card, that is a state of the game. And this down here, so for example, if you have a total of 8 and the dealer has a 5, you should hit. That is the action that you should take to get the maximum possible reward out of this game. So this is a provably optimal policy for blackjack. Now, we're discounting things like card counting, etc. But if you play this, you will do as well as you possibly can at blackjack. And then we can show that if you do play optimally in blackjack, you are losing 2% of your money every bet on average, right? So if you're going to lose 2% on average every bet, why would you play the game? I don't know. Maybe you're having some fun, a few drinks, whatever. But it's just the idiot tax. That's what gambling is, right? That's what people call it. But it's really the uneducated tax. You're going to play this game. Maybe you get lucky. But on average, you are sitting down at that table, and every time you put money in, you know you're going to lose 2% of it if you play an infinite amount of hands. So if any of your cousins or uncles or whatever say that they have a system to beat the casino, there's a reason the casino has $1 billion, right? And it's not because your uncle has a system. All right. Policies could also be implemented as if-then statements, and we can view if-then statements as flowcharts, right? So there's interesting things we can do. So here was my policy this morning. The alarm rings. Are you ready to get up? Hell no. Hit the snooze button. An average of 3 times. That's way too low for me. I've hit the snooze button like 10 times before and not even remembered it. I don't know if you have that same problem in the morning. Oh, I'm ready to get out of bed, climb out of bed, end. Here's one of my favorite ones, which is the basically worrying does nothing flowchart, right? Do you have a problem? No? Okay, well then don't worry, you don't have a problem. If you do have a problem, can you do something about it? Well, if you can't do something about it, then whatever, don't worry, right? It's going to happen. If you can do something about it, then do the thing and stop worrying. So that's it. Everyone's anxieties are solved, right? No problems anymore. Okay, new concept. I told you there were going to be a lot of definitions in that class. Yeah, question.
What's the difference between policy and an agent function?
So the agent function, let's say we're doing reinforcement learning. Oh, the question for the mic was, what's the difference between an agent function and a policy? They're very similar. You can think of the agent function as the agent's current policy, which if we are doing something like learning, will change over time. Right? So the agent function is the thing that makes the decision. And then if we apply the agent function to every possible state and write it down, then we have a policy. Right? So the agent function doesn't inherently encode every possible state. It's just you pass in a state, it gives you an action. But they're very closely related concepts. That's a good question. Okay, rationality. So a rational agent is one that does the optimal action for every possible state. But what makes it the optimal action? Well, first, it's the thing that makes the agent the most successful, right, in whatever performance measure that we have to define. So one agent may do something and get some result. Another agent may do something else and get a different result. We have to compare those somehow. In AI, no matter what the problem is, the specification, whether it's an LLM or a search algorithm or an if-then statement, it all boils down to one number. That number might be the error rate. It might be the amount of points scored. It might be the amount of money won in a blackjack game. But there's nothing magic about AI. In the end, it is trying to maximize or minimize a single thing. And that is the performance measure that you, as the problem solver, have to define somehow. And so the rational agent, therefore, has an optimal policy. But optimal within its level of knowledge. And we'll talk about what that means in a second. So the performance measure is a criteria for success of an agent. So if you write a paper and say, my new algorithm is better than the old algorithm, you will show that your performance measure, your agent performs better within that measure than some other agent. It can also be called an evaluation function. And so we have evaluated the agent's behavior somehow and found it to be X. We found the error rate to be Y. Here's a typical scenario. An agent is placed in an environment. It has some agent function. It performs a sequence of actions. The actions cause the environment to go through a sequence of states. If the sequence of states is desirable and the agent has performed well, then the evaluation is higher. Right? This is kind of the essence of learning. Now, I know this is not strictly a machine learning course, but this is the essence of reinforcement learning. We're going to say, and this is the second half of the course, do something. See how it turned out. If it was good, the next time you see that scenario, do the same thing. If it was bad, next time you see that scenario, don't do the same thing. Right? So this is one of the processes of learning. So here we have a performance measure. Who knows this game? Flappy Bird. Right? You just hit the button and you move up or down. You try not to hit the pipes. Very, very, very easy performance measure. It's the x-axis. Right? How far to the right have you gotten? What's your high score? In other problems, like, for example, in pathfinding, we may want to know the shortest path between two locations. If you're doing something like, there's an interesting story from, I think it was UPS or FedEx or one of these delivery companies. They found that, their GPS system that they have, it's all custom. And at first, they were just doing shortest distance. Right? I want to get from point A to point B. That seems pretty intuitive. I want to get to the delivery place in as little distance as possible. Turned out that wasn't best for business. Why? Because sometimes the shortest distance keeps you waiting at a red light for 4 minutes trying to turn left. Right? So they actually did some cool stuff with their algorithm where sometimes, instead of waiting for a left turn, they'll just make 3 quick right turns. Right? So they tweaked their algorithm to optimize fuel efficiency instead of distance. Because if you're waiting around, you're still burning fuel, and they ended up saving something like 7% of their fuel costs, which is insanely high if you're talking about a company like UPS. So, the thing you think you're trying to solve for at first may not be actually the best thing in the long run. But the same algorithm, ideally, should be able to solve for both performance measures. Here with the pole balancing problem, the performance measure is how long is it being balanced for. For a lot of games, the performance measure is just win the game. I played against you and I won 4 out of 6 times, so I have a 66% win rate. That's greater than 50%, therefore my agent is smarter than your agent. So rationality depends on 4 different things. It depends on the performance measure that we just talked about that defines the success, the agent's prior knowledge of the environment, the actions that the agent can perform, and the percept sequence. This is what defines rationality. The agent that does the best that they can given what they know. But rationality is not omniscience. So omniscience is another definition, which is like, I guess, an omniscient agent, I guess in colloquial speak, would be like a deity or a god, right? They would know everything. They can see through things. They just have the complete, unrelenting state of the universe in their brain at all times. So an omniscient agent would know the outcome of actions. So for example, okay, I have an example in a second. It would know the outcome of randomness. Sometimes maybe you're rolling a dice or dealing a card. It would know the entire state of the environment. An omniscient agent is not a rational agent does not mean an omniscient agent, meaning they know everything. They're doing the best that they can with the knowledge that they have. So, if I bet you in front, blue shirt, okay, so I tell you I have a die, like a dice, a 6-sided die. I'll bet you $100 that the die will roll between 1 and 5. So if it's between 1 and 5, you get the $100. If it's a 6, I get the $100. Would you take that bet? No?
Yeah.
Oh, you would? Why?
Because I have the more possibility.
Yeah. So we'll talk about this a bit later, but we'll talk about this thing called expected value, right? When it comes to randomized actions, on average, how well do I expect to perform? And so, if you did take that bet, and I rolled it, and it came out a 6, was your bet still rational?
Yeah.
Yes, you still made the best decision. Now, other life factors, if that was your last $100 and if you lose, you're going to sleep on the street, we're factoring that. Let's say you have infinite money, just expected value. But the bet was still rational because the expected value of that bet is very large. And this is one of the things that I hate about, televised sports, right? Is when some football player makes a Hail Mary throw that had a 1% chance of working and wins the game, instead of taking the safer play that maybe could have tied or something. That play, if it works, they're a national hero. If it doesn't work, they're a laughingstock and they're about to get fired. Why? Why does the public perception of a person or a sports team depend on the outcome of something? It should depend on the expected outcome of something. That person took a 1% chance and got lucky. That doesn't mean they're smart or good. It means they got lucky. There was maybe another bet, right? So whenever you hear someone yelling at a sports outcome, tell them to think about the decision, right? Was the decision smart? And yes, all the money is won or lost on the outcome. I understand that. But as academics and rational people, if that game was played 100 times, they're going to lose 99 of them, right? So just keep that in mind. Alrighty, on to environments now that we know about agents and actions and policies, etc. So the task environment is essentially the problem. So when you go to solve a problem, you're essentially defining the environment in which you'll take actions, etc. A rational agent for that problem is going to be the optimal solution to that problem. So the specification of the properties and an environment greatly impact the design of a rational agent that's going to act within it. And the design meaning, what algorithm am I going to choose? What actions am I going to be able to do? What discretization of the state space might I do, etc. And just remember that a state is a particular configuration of a given environment. So let's take the example of chess. It's a great example. Everybody knows it. So the environment so here's the chessboard. Here is all the different chess pieces that there are. So the environment of the game of chess involves several different things. It involves the rules and the boundaries of the game. So for example, I am only allowed to place pieces on that grid. The grid is essentially the whole universe of the chess game. There are going to be the legal actions that I can take. So, the bishop can move diagonally and can't move through other pieces. The rook is going to have these moves. The queen has these moves. The king has these moves. No, I'm not going to go through all the rules. But the legal actions are an important part of the environment. Also, there has to be some sort of initial state to the environment. I actually forgot the moves for a rook there. The up and down is the rook. Yeah. The knight is the one that goes over 2 up 1. That's embarrassing. So, other than the starting state, I'm sure you could all put the pieces in the starting state of chess. The pawns go here, the other pieces go here in a particular order. There will also be the goal condition or the goal state, right? So sometimes there is a goal state. I want to go from here to my bed and have a nap. So the goal state is me in bed. Here, there is no goal state. Why? Because the condition of the goal is to be in checkmate, right, or a draw. But typically, it's a checkmate. And so sometimes we don't have a goal state that we can check for, meaning is this state equal to this other state? We would have to say, is this condition satisfied on this state? So are they in checkmate? Are they in one of the green squares, etc.? So for example, this is the starting state of a game of chess. There's a variant of chess which is really fun. It's called Fisher random chess. And in Fisher random chess, you randomize the places of all the pieces of the back row, and it gives chess a bit more replayability, we'll say, if you're bored with the game. Here is an arbitrary state of the game in the middle of the game. So random mid-game position of chess. Now, keep in mind that there are some configurations of chess pieces on a board which are not actually legal configurations of chess pieces, right? So just because you have pieces and a board does not mean that any random configuration is actually a state of the game of chess. Some states are impossible to get into, and you would exclude those from those scenarios. So for an agent, the state of the environment is based on the observation that it can make, right? We already talked about that. That observation may not be a complete representation of the environment state, because, you know, something may be hidden behind that thing that I can't see. There might be another student over there who's, I don't know, going to jump me or something like that. The agent's observation is all that it can make to use to make a decision. Now, of course, it's knowledge, etc. But in terms of the configuration of the environment, it is given to us in a specific way that may or may not contain all the information. So, for the game of chess, the agent can observe the entire environment. It's all there. You can make the optimal decision. For an environment like self-driving cars, you may not be given the entire state of the environment, right? When you're driving, sometimes you can see the car in front of you, like 2 cars ahead. Sometimes you can't. Sometimes there's a turn in the road, right? How many times have you been stuck behind someone driving really slow, but there's a turn? And if you try and get around them, maybe there's a car coming and you get hit, right? So you're not always going to be given the full state of the environment. So in a self-driving car, you may be given some sort of laser range finding or sonar or vision system, etc., but you can never know absolutely everything that's going on. Given all that, there's a concept which is the state space or the action space. The state space is a measure of the number of possible configurations of the environment for a given problem. So for example, how many different ways can we configure a chessboard? An action space is a measure of how many actions are possible from a given state. Typically, it's given as the average or the worst case, right? So in a game of chess, let's just say at any given time, I can do approximately 50 different things, right? I have a bunch of pieces that can move to a bunch of different spaces. And these are used as an estimation for the complexity of a problem. I say estimation because it doesn't prove something is complex. It just shows, okay, if I have a state space of 10, I can just trivially enumerate all the possible ways to play that game and decide on the best thing to do. But if I have a larger one, you know, it's 10 to the 100, well, I couldn't possibly compute that. There may be a simple solution to that game that has a state space that's very large, but we would have to figure that out in some other way. Let's look at an example. Tic-tac-toe, or noughts and crosses, state space calculation. At any given place on a tic-tac-toe board, there's either an X, an O, or a blank space. That means there is 3 possible ways to put a piece at any given state, and there are 9 spaces. So 3 to the power of 9 is approximately 10 to the power of 4. So there's a few thousand different ways to play, or sorry, a few thousand different ways to configure X's and O's on a tic-tac-toe board. And so what we do sometimes is we just state that number, which is the exponent after the 10. So the state space complexity of tic-tac-toe is 4 or 10 to the power of 4. So, knowing that, how would you solve a game of tic-tac-toe? You do not need deep neural networks. You do not need OpenAI, LLMs, ChatGPT. What would you do? I'm just going to look at all the possible things I could do in this game and pick the best one, right? It's a measure of an approximation of complexity. And what it tells you is, if you can do that many calculations in a reasonable amount of time, then you can solve the game. It's not very complex. Let's look at chess. All right, there's a lot of details here. I'm not going to go into all the details. 64 places on the board, 32 empty board spaces, 8 pawns in 2 sets. There's some combinatorics going on here behind the scenes, but the rough calculation is approximately 10 to the 42. Okay? So approximately 10 to the 43 or 10 to the 42 possible configurations of chess pieces on a chessboard. Now, some of them are not legally observable, right? They're not actually obtainable in a normal game of chess, but this is an upper bound of the complexity of the game. So 10 to the 42, what's that? Some number that I don't even know what it is. It's a lot more computations than I can do, and I'll give an example of that in a bit. So we could not trivially solve the game of chess by just enumerating everything. Let's look at the game of Go. Go is an Asian board game. It's very popular in Asia, not so much in North America. There are white stones, black stones, and blank pieces, a 19 by 19 space, and so you can configure 3 different possibilities, 3 to the power of 361. That is 10 to the power of 172. We are very bad as humans at knowing how big that number is, but I'll try and visualize it for you in a second. So when we talk about state space complexity, you would have tic-tac-toe, okay, there's approximately 10,000. Chess, 10 tradecillion. And then I'm not even going to pronounce this made-up word for Go. It doesn't even matter at this point. After a certain number, it's just big number here, right? It's pretty safe to say that we will not be able to compute that in our lifetimes. That was state space complexity. Now we have game tree complexity. What the hell are you talking about? Okay. State space complexity is the number of configurations of an environment. So it's the number of possible chessboards there are. Game tree complexity is the number of ways to take a sequence of actions through the game. And so some states may be reachable via multiple different action paths. Okay, so let's have an example here. Someone who hasn't raised their hand yet, how many different ways, so this is a single state of the game of chess, but how many different ways can I reach this state in the game of chess? No wrong answer, just any one. Yep. Why? Exactly, right? So this is an example. Even though this is a single state of chess, now one may take, okay, let's take the theoretical maximum of infinite, because I could just keep moving this piece here, 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 right? That's not a realistic game of chess. If we take a more realistic game of chess where no move duplications have happened, then I could have moved this piece first, or this piece first. Then for either of those, the other player could have moved that one or the other one, right? So there's some number of ways to get to this state in a reasonable way. And so the whole point here is that the number of ways to move pieces through a game is exponentially higher than the number of resulting states of that game, right? So that's the game tree complexity. Same thing for this. There are many different ways that I could achieve that state of tic-tac-toe via me placing here first or there first, etc. So the game tree complexity is even cenovemdecillion, okay, whatever that number is. It's way bigger, right? So this is a way of looking at the game and saying, okay, I cannot just trivially apply a brute force algorithm to look at all of these combinations and come up with it. Let's try and figure out how big these numbers really are. Okay, 10 to the 9. This is the number of seconds in a century. So that's 10 to the 9. I'm drawing 9 dots here. This is the number of humans born in history, right? 10 to the 11. Here's how crazy exponentials are. Going from 9, which is the number of seconds in a century, to only to 17, now we're talking about the age of the observable universe, right? Just by going 10 to the 17. Okay, so these numbers are starting to look pretty big. The diameter of the universe in meters, 10 to the 26, right? So if we go from this, if we go 1 meter per second, you cannot traverse the universe in the amount of time the universe has been around. Just interesting questions like that. 10 to the 30, approximately the number of stars in the universe. 10 to the 80 is the number of atoms in the universe. 10 to the 122 is the number of protons needed to fill the universe. That's not the number of protons in the universe. That's if, like, we wanted to literally fill the universe, all the infinitely small space with protons, that's the number we'd need. So, if we had a full universe of protons, each with a supercomputer inside it, they would have to do 10 to the 50 calculations per second to, like, enumerate all of Go, right? So I don't think that's a reasonable amount of time. Oh, and this is the Go game tree complexity. This is way higher than that, right? You had a question.
Why do we care about the game tree complexity of these games like Go and chess and tic-tac-toe, where we only care about the current state?
Because you have to actually traverse through a game to play against an opponent, right? And so if I can't just enumerate through all possible states of a chess game in order to, how do I explain this? If I give you a board state and you want to know what the best move is from that state, if you apply one of these search algorithms that we will be learning about, it does things like, okay, for every move that I could do, for every move that you could do, for every move that I could do, and it tries to see that like a human sort of plays, right? And so you wouldn't just say, okay, what are all the random states of chess? Try and put me in one of those. You're actually in a state, taking actions, getting to a new state, going on. And so the number of ways to go through the game tree is one of the ways that we try and solve that problem. And that is actually a much bigger problem than it seems. That'll become much more obvious once we get into the search part of the course. And for a game like StarCraft, which is what I like to study, there's a lower bound of like 10 to the 1,000. It doesn't even matter what these numbers are anymore. They're essentially just showing that the game is very hard. But it is important, very important, that a large state space does not prove that a game is complex. Okay? So I'm going to show an example here. So the game of Go, who knows the rules to Go? Does anyone here? Okay, so one person. So in Go, you take turns placing black stones and white stones, right? And if you completely encircle a group of stones from your opponent, you capture them, and they are removed from the board. And then the space where they were, the opponent can no longer play there. So it's a game of territory capture. And then when there are no longer any legal moves on the board, whoever has the most pieces on the board wins. So you're trying to capture pieces of the enemy. But consider this. Consider a variant of the game of Go where instead of capturing, so remove the capturing from the game. If you remove the capturing from Go, then essentially all you're doing is taking turns placing pieces on the board. And so who wins the game? Whoever went first. Because they placed the first piece, there are an odd number of places on the board, and so they'll also place the last piece. So just by slightly modifying the game, the state space complexity of that modified game of Go is the same. There are still 10 to the 172 possible states, and there are still 10 to the 360 possible ways to play that game, but the solution is trivial. It is not a complex game, because we've found some sort of analytical solution to the game. So state space complexity, action space complexity, game tree complexity it's a way to say you can't trivially solve it by enumeration, but you may be able to solve it via other ways. And I just showed that example. I should have just went to the next slide. All right. So the environment definition then is the rules and dynamics that govern the game, the legal actions allowed at any state, and the initial and goal states, usually given by the problem instance. And environments have properties. And I only got 10 minutes left, and the recording cuts off at exactly 3:15. So I'm going to save questions till the end, because I got to get through a bit more material. I rambled for a bit too long. First property. Is it fully or partially observable? Fully observable means that the sensors we have given the agent give it complete access to the state. And so in games, this is called a perfect information game. Fully observable, pretty pretty obvious. Partially observable means some of the data in the environment is hidden or occluded. The sensors may be noisy. This is called an imperfect information game. Here's an example. Chess is perfect information. I can see everything. A game like StarCraft, there are certain parts of the map that I cannot see, so it is imperfect information. Next is deterministic versus stochastic environments. Deterministic essentially means that there is no randomness. So if I'm given a state, and I'm given an action to perform at that state, I will always go to this next state. So there's no randomness. The next state is entirely determined by the current state and the action. In a stochastic environment, there is some uncertainty about the outcome of actions. There might be a dice roll. Maybe I land on Go, I collect $200, or I go to jail in Monopoly, right? There's some uncertainty. And think of that from the point of view of the agent. Is the agent in control of the randomness? No, then it's a stochastic thing. So chess is just the canonical example of perfect information. It is deterministic. There is no randomness. Imagine the game of chess where when you tried to take a piece, you had a 50-50 chance of taking it or them taking you. Well, that's an interesting game. But in a game like of many games of cards, there's the random shuffling and dealing of the cards, right? So that's an example. Episodic versus sequential. Episodic tasks are divided into atomic episodes, where the agent perceives the current state, takes an action, and the next episode does not depend on the previous. Most games, or most environments, are actually sequential, where my current action is going to influence future actions, and my actions may have long-term consequences. So what is an episodic task? It's something like recognizing a handwritten digit, right? The next time I try and identify another digit, it does not depend on the action I took at the previous one. It's just a new sample. It's episodic. Sequential would be, okay, if I move a piece here, on my next turn, now my legal actions are different. And so a sequential game, my actions have future consequences. Dynamic versus static. Dynamic environments may change while the agent decides what to do. They are continuously asking the agent what to do, like a real-world robot, right? If it's about to go off a cliff and it doesn't do something, it's going to go off the cliff. In a static environment, the environment only changes when the agent takes an action. So decision-making time wouldn't matter. So a game of chess, the pieces aren't moving around. Now, you may have a game of chess where you have a clock, so let's just ignore that. But the decision time-making doesn't matter. In games, these are called real-time games. Those are dynamic. And turn-based games, which are static. So over here, in any video game, you know, if the enemy's coming at you, they're not waiting for you to make more units or make defenses. They're going to get you. Versus in chess, you can take all the time you want to think about the next action, unless it's a timed game. Discrete versus continuous. This is applied to the state of the environment. It determines the way time is handled. Discrete, basically, we're only, in your lifetime, you're probably only ever going to be dealing with discrete problems. Finite number of distinct states, discrete sets of percepts and actions. Continuous would mean like continuous time, continuous actions, like a real-world problem. But in order to solve a continuous problem, because we're using discrete computers, we actually need to translate continuous problems into discrete problems. So again, discrete problems are all the things we've talked about, but an actual problem that is continuous would be something like a self-driving car, but we do need to chop it up into discrete states in order to apply computation to it. Single agent versus multi-agent. In single agent, one agent is acting at a time. This might be something like solving a crossword puzzle or pathfinding through a maze. In multi-agent, you have multiple agents acting together, either cooperatively or competitively. And so once we get to, we'll talk about single agent search first, and then we'll talk about adversarial search, where two agents are competing in a given problem. So over here, we have a single agent problem with its pathfinding. Over here, we have this multi-agent problem, which is like a team-based video game or something like that. We have complete versus incomplete information. In complete information environments, all of the game rules and physics are known, and all possible actions are known. Okay? So complete information, that's what that is. In incomplete information, the game rules or physics may not be known, and actions may have to be discovered. Right? So someone didn't tell you the rules to chess. You're just trying to make actions. Right? So there are two different things here. One is, what did I call it? there's observability. That's different from complete versus incomplete information. Okay? So just keep that distinction in mind. In this course, we're not going to be talking about incomplete information things. That's like real-world problems where we don't know exactly how the physics works, etc. So here's a little chart for the end. Thinking about these properties of game environments, each of them has sort of an easier mode and a harder mode, right? So if we look at solving a crossword puzzle, what are the properties of solving a crossword puzzle? Well, that is a sequential problem because the words I write down at the beginning will influence what I can write down at the end. It's single agent, deterministic, fully observable, static, and discrete. Let's make the problem a little harder by changing single agent to multi-agent, right? If we have more agents, that makes the problem a bit harder. So chess, it's still deterministic, fully observable, static, and discrete, but now it has multiple agents acting at the same time. So in whatever algorithm I apply, I now have to consider the choices that the other player can make as well. Let's make the game a bit harder by introducing randomness. So we have a game like backgammon. So backgammon is a board game where you move pieces based on the result of a dice roll. So now I have to say, okay, if I'm going to roll this, I could do this, but if I roll this and then my opponent rolls this, there is uncertainty about the things that can happen in the game. But it's still fully observable. We can see where all the pieces are. Now let's go to a game like poker, right? In a game like poker, I cannot see my opponent's cards. And so it's no longer a fully observable game. It's a partially observable game. And that introduces other problems. Then let's move up to video games because they're dynamic now. So no longer can I take all the time in the world to make a decision about my poker hand. I've got to act right now. It's a real-time game. And so this is a dynamic. And then if we change discrete into continuous, we're all the way into like the real-world problems where we've got to act as fast as possible, and it's actually continuous action space, so I need to make decisions. Like in a game of StarCraft, for example, I will be given, here's the floating point XY location that you actually are in the game. But in the real world, I have to make noisy measurements about continuous spaces. Do I store that in a float? Do I store it as an int? Do I store it as a double? Whatever. There are precisions when I go to translate a continuous space into a discrete space. So that's it for the lecture. One quick note before we go, though, is that please go do the quiz for the course. Like 20 people have done it so far. You can attempt it any number of times. So if you get something wrong, like I know you all know the answers to it, but please just get that done and out of the way. If you get one of them wrong because it was a little bit tricky or you couldn't find it in the table, just do it again. I just want everyone to get 100% on that so I know that you know what's going on in the course.